Tonight begins with a question a child might ask, and ends somewhere no adult has ever been. How long would it take us? You, me, anything we have ever built, to travel 1 light year. Light crosses that distance in a single year, moving faster than anything in the universe. We cannot, not yet, but tonight we are going to try anyway, slowly, one vehicle at a time, from a pair of walking shoes to a sail pushed by lasers, climbing a ladder of speed that ends just short of light itself. Along the way, the numbers will grow too large to hold, and that is fine. You are not here to hold them. Dim the lights if you like. Let the day set itself down. There is no test at the end of this journey, and no hurry anywhere inside it. The stars have waited billions of years for someone to ask this question. They can certainly wait one more quiet night while you drift. Let us begin. At walking speed. Before we can ask how long it would take to travel 1 light year, we have to be clear about what a light year actually is, because the name itself plays a small trick on almost everyone who hears it. It sounds like a measurement of time. It is not. A light year is a measurement of distance. It is the distance that light, the fastest thing that exists, manages to cover in 1 full year of travel. And the reason astronomers invented such a strange ruler is simple. The ordinary rulers we live with, miles and kilometers, simply give up when you point them at the sky. The numbers grow so long that they stop meaning anything at all. So before any vehicles arrive, we are going to build this ruler together, piece by piece. Out of things you already know, start with something small. Start with this room. When you flip a light switch, the light seems to fill the room instantly. It does not. Of course, it takes time. An unimaginably small sliver of time. But our eyes and our minds are far too slow to catch it. So we experience light as something that simply appears, everywhere at once, free of charge. That everyday experience is exactly why the true speed of light is so hard to feel. We have never once seen light travel. We have only ever seen it arrive. So let us slow it down in our imagination and actually watch it move. Physicists have measured the speed of light with extraordinary precision for well over a century, and the answer comes out to about 670 million miles per hour, a number that size slides straight through the mind. So, here is the same fact wearing more comfortable clothes. In the time it takes you to say the words 1 second, a beam of light could circle the entire Earth about 7.5 times. 7.5 trips around our whole world, every ocean, every mountain range, every city where anyone you have ever loved is sleeping tonight. In a single second. Say it again. Slowly. 1 second. 7.5 laps around everything. Hold that pace in your mind. And now let the beam leave the Earth entirely, because the character of the journey is about to change. The Moon is the closest world to us, the only other place human beings have ever stood. Light makes that trip in about 1 1/3 seconds. When the Apollo astronauts spoke with Mission Control in Houston, their voices, riding on radio waves that travel at the speed of light, needed more than a second to cross the gap. There was a pause stitched into every conversation between the Earth and the Moon, and nothing in the universe could remove it. Not urgency, not engineering, not homesickness. The distance itself demanded that silence. And the distance was paid. Every single time. In seconds, push farther out. The sun, the star that every living thing on this planet depends on, sits about 93 million miles away. Light needs a little more than 8 minutes to cross that distance. Sit with what that means, because it means something quietly wonderful. The sunlight warming your face on any given afternoon is always a little more than 8 minutes old. You have never once seen the sun as it is. You have only ever seen the sun as it was. 8 minutes ago, if the sun somehow winked out this instant, the afternoon would go on, golden and ordinary, for 8 more unhurried minutes before anyone on Earth had the slightest idea. The sky does not show us the present. The sky is, and has always been, a very beautiful kind of history. Now, and this is the moment the whole night turns on. Keep going. Let the beam of light race past the sun and simply continue. At that same impossible pace. 7.5 Earths every second. Minute after minute. Hour after hour. After about 5.5 hours, it passes the orbit of Pluto. The small, cold world that many of us grew up calling the edge of everything. And the light keeps going. It flies on through the dark, day after day, week after week. A month passes, it is still going. 3 months, 6 months, still going. Never slowing, never resting, never needing so much as a breath. 7.5 Earths, every single second, the entire time. Autumn turns to winter somewhere behind it. Winter turns to spring, and only when a full year has passed, only then, has that beam of light finally crossed the distance we call 1 light year. If you want the number, here it is, stated once and then set aside for the rest of the night. 1 light year works out to nearly 6 trillion miles. Trillion, with a T. But I promised you at the start that you would not need to hold the numbers. So do not try to picture 6 trillion of anything. Nobody can. Picture the year instead. Picture everything a single year contains. 4 full seasons. A birthday, somewhere in it. Probably. A day that changed you. And a few hundred perfectly ordinary evenings, like this one. Now imagine the fastest thing in the universe, spending that entire year, every second of it, in flight, just to cross this 1 unit of cosmic distance. That is the ruler. That is 1 light year. Not a number, a duration of pure speed. And here is the gentle twist the whole journey rests on. 1 light year is, by the standards of the galaxy, a very short distance. The nearest star system to our Sun, a triple system called Alpha Centauri, sits more than 4 light years away. The galaxy we live in stretches roughly 100,000 light years from edge to edge. Astronomers did not invent the light year to describe the far side of the universe. They invented it to describe the neighborhood. It is the smallest ruler that works out there, the cosmic equivalent of measuring your own street. And even this smallest ruler is built from a full year of light in flight. So tonight's question, the question a child might ask, turns out to be sharper than it first sounds. How long would it take us to travel 1 light year? Not to Alpha Centauri, not across the galaxy, just this, the single shortest unit on the map of the stars. Light does it in a year. What can we do with our legs, our machines, our rockets, our cleverness, and our patience? Here is how we are going to find out. We are going to climb a ladder, 1 rung at a time. On the lowest rung waits the oldest vehicle humanity has ever owned. A pair of walking feet. Above that come our cars and our airplanes. Then our rockets. Then the fastest objects our species has ever built. Machines that are flying right now. Tonight. Through the dark, beyond the planets. And higher still, we will find the machines we have only drawn on paper. Sails pushed by beams of light. Ships designed to carry generations. Ideas that lean right up against the speed of light itself. At every rung, we will ask the same simple question. The question that will become the heartbeat of this whole night. At this speed, how long would it take to cross 1 light year? And at every rung, the answer will teach us something. Not just about distance, but about what kind of travelers we actually are. There is no need to climb quickly. The ladder is not going anywhere, and neither is the distance waiting at the top of it. If your thoughts have already begun to loosen and wander, that is not a problem. That is the point. Everything important tonight will be said slowly, and more than once, in different ways. So take one unhurried breath and step onto the lowest rung with me. Forget the rockets for now. Forget the lasers. We are going to begin this journey the way our species began every journey it has ever taken. Long before it had wheels. Long before it had wings. Back when the horizon was the only map anyone owned. We are going to walk. Every journey our species has ever taken began the same way, with one foot placed in front of the other. Long before we had wheels. Long before we had sails. Long before anyone imagined that a horse could be ridden. Walking was not just a way to travel. It was the only way. Every migration, every discovery, every early map of the world was drawn at roughly 3 miles per hour. The ordinary, unhurried pace of a human being crossing open ground. Rivers were named by people who arrived on foot. Mountain passes were found by people who walked until the ground stopped rising. For tens of thousands of years, 3 miles per hour was not a speed. It was simply what the world was made of. So, it is only fair that our ladder begins there. On the lowest rung, with the oldest vehicle we own, let us set the scene. Imagine a path, perfectly straight and perfectly smooth, stretching away from your front door and rising softly off the earth, out past the moon, out past the planets, aimed at a point 1 light year away. Imagine you could walk it the way you would walk a quiet country road on an autumn evening. The light going amber, the air cooling, nothing to think about but the next bend. No need for food or water in this thought experiment. No weather, no blisters, no nightfall, just you, walking at 3 miles per hour, hour after hour, never stopping. This is not a plan. Of course, nobody is proposing it. It is a measurement wearing the shape of a story, a way to let your body feel a distance your mind refuses to hold. So, at this speed, how long would it take to cross 1 light year? Here is the answer, and I encourage you to let it wash over you rather than trying to grip it. Walking without a single pause, day and night, at the pace of an evening stroll, you would need more than 200 million years. 200 million years. A number that large slides right off the mind. So let us give it something to stick to. 200 million years ago, there were no birds anywhere in the sky, because birds had not yet evolved. There were no flowers anywhere on earth, because flowering plants had not yet appeared. There was no grass, not one blade of it, anywhere on the planet. The continents themselves were still joined in a single enormous landmass that was only beginning to crack apart into the shapes we know from our maps, so that a walker could have crossed from what would one day be Africa to what would one day be America without ever seeing the sea. And the dinosaurs, having survived a great extinction at the end of the Triassic period, were just beginning their long rise to rule the planet. Now, put a walker on that path, on that ancient day, and let them walk. They walk through the entire age of the dinosaurs, a span so long that the dinosaurs themselves had ancient history, species rising and vanishing and being replaced, while the walker simply continues. They walk while the great land mass splits and the Atlantic Ocean opens up behind them, an ocean being born like a slow crack in a plate. They walk on the day the asteroid falls, and the sky goes dark, and the giants vanish from the earth. They keep walking through the long, quiet aftermath, through the rise of the mammals, through the raising of the Alps and the Himalayas out of colliding continents, through ice ages that come and go like weather. They walk while our own ancestors climb down from trees, and stand up, and learn fire, and speak, and paint, and farm, and build, and write. They walk through every empire that has ever existed and every one that has ever fallen. They walk through the invention of the wheel, the printing press, the telescope, the airplane, the internet, and only tonight, at last, after every single one of those things, would that walker finally arrive at the 1 light-year mark. And remember, that is the version of the walk with no rest at all. A real walker, someone who slept each night and walked an honest 8 hours a day, would need roughly 3 times longer, more than 600 million years, a span reaching back beyond nearly the whole history of complex animal life on this planet. Let that settle for a moment, and notice that it does not need to feel discouraging. Nothing about tonight is a race we are losing. This first rung of the ladder exists for one reason only: to give your imagination an anchor. From now on, every faster vehicle we board will be measured against this. The walking speed of a species, the pace at which our ancestors crossed continents and peopled the entire earth. 3 miles per hour was enough to give us the whole world. It is simply no match for the space between the stars. And there is something almost tender in that fact. Once you turn it over, the scale of the galaxy is not a judgment on us. It is not the universe finding us too slow. It is just the true size of the room we happen to live in. And rooms do not insult the people inside them. Before we climb to the next rung, hold on to one last image from this one, because it will matter more than the number. Anthropologists who study ancient human migrations believe our ancestors walked out of Africa and, over tens of thousands of years, reached nearly every habitable corner of the planet. They crossed deserts, they crossed mountain ranges, they crossed land bridges that no longer exist, ground that is now seabed, following coastlines and animal herds, and, one imagines, ordinary curiosity. And they did it all at 3 miles per hour. Not one of them ever saw the whole journey. No single person walked from Africa to the far end of the world. Each generation simply walked its own stretch of the road, made a life somewhere along it, and handed the horizon to its children like an heirloom. The journey was completed by people who never met each other, most of whom had no idea they were part of a journey at all that is worth carrying up the ladder tonight. Because patience is the one resource our species has never once run out of. And this old, slow, 3-mile-an-hour instinct, the willingness to keep going towards something you will not personally reach, is going to reappear on almost every rung above us. In the strangest and most modern forms, it is going to show up in a filing cabinet in San Diego. It is going to show up in a spacecraft flying tonight with a golden record bolted to its side. For now, though, let the walker rest at last. Somewhere on the imaginary road, in no particular hurry, under a sky full of stars nobody has named yet. Climb one rung up the ladder now, and suddenly the path is paved. The vehicles on this rung are the ones that fill our actual lives. The car in the driveway, the airliner crossing the night sky with its small patient blinking light, the record-breaking aircraft of the last century. These are the machines that shrank the Earth, that turned oceans into afternoons and continents into weekends. Tonight we are going to aim each one of them, gently and impossibly, at that same point 1 light-year away, and watch what the distance does to them. Start with the car, because it is the machine most of us know best. Picture a long highway drive at 60 miles per hour. The kind of steady cruise where the road hums beneath you and the mind drifts pleasantly out the window. 60 miles per hour is 20 times faster than walking. And on Earth, it feels like genuine freedom. A single day of driving can carry you into a different climate. A week can carry you across the entire United States, from one ocean to the other, through deserts and cornfields and cities you will never visit again. So point that car at the stars. Settle into the seat. Set the cruise control, and never touch the brakes. At this speed, how long would it take to cross 1 light year? A little over 11 million years. 11 million years behind the wheel. The walk took more than 200 million. So, the car is a magnificent improvement. And yet feel how far away the finish line still sits. 11 million years ago, our own ancestors had not yet parted ways with the ancestors of gorillas and chimpanzees. The entire human story, every language ever spoken, every city ever raised, every song ever sung, fits into a small corner at the very end of that drive. We made ourselves 20 times faster, and the destination barely stirred. So we leave the road and take to the sky. A modern commercial airliner cruises at roughly 575 miles per hour, nearly 10 times faster than our car. This is the speed at which most of humanity now experiences great distance. The speed of visiting family across a continent. The speed of oceans sliding by beneath a small oval window while dinner is served on a folding tray. It is fast enough that the Earth genuinely feels small from up there. Small enough that you can watch a whole mountain range pass in the time it takes to finish a paperback. So aim that airliner at our distant point of light, keep the seatbelt sign off, and settle in for the longest overnight flight ever scheduled. At this speed, how long to cross 1 light year? More than 1 million years. 1 million years in seat 32A. The cabin crew would come down the aisle with dinner hundreds of millions of times. And notice what is quietly happening as we climb this rung. Each new machine multiplies our speed. And each time, the answer only sheds a 0 or 2. falling from hundreds of millions of years to 11 million to 1 million. The distance is absorbing our finest everyday machines the way the ocean absorbs raindrops. Very well. Then let us fly faster than sound itself. In the 20th century, engineers built aircraft that broke the sound barrier and kept going. The famous Concorde carried paying passengers across the Atlantic at about 1,350 miles per hour, more than twice the speed of sound. On evening flights heading west, it could outrun the turning of the Earth, so that passengers who took off after sunset could watch the sun climb back up out of the horizon ahead of them. An ordinary evening running backward outside the window. At Concorde speed, 1 light-year would still demand roughly 500,000 years of flight. And at the very top of this rung sits a machine most people have never heard of. A black rocket-powered aircraft called the X-15. It was a joint project of NASA and the Air Force. And it did not take off from a runway at all. It was carried aloft under the wing of a bomber, dropped like a stone at high altitude, and only then lit its rocket engine, burning for a minute or two of pure violence before gliding back down to a dry lake bed. It flew so high and so fast that several of its pilots earned astronaut wings without ever riding a rocket off a launch pad. In 1967, a test pilot named William J. Knight flew the X-15 to about 4,500 miles per hour. According to NASA's records of the program, and in all the decades since, no airplane has ever carried a human being faster. Give that record-breaking machine our impossible mission. Hold it forever at its best speed. And ask the question of the night. At this speed, how long to cross 1 light year? Around 150,000 years. 150,000 years. Pause on that number, because it is the first one tonight with a genuinely human shape. It is far longer than all of recorded history. Writing, agriculture, cities, nation, every empire that has ever risen and crumbled, all of it together fills only a small fraction of such a span. The fastest wings we have ever built would need to fly through dozens of complete rises and falls of civilization just to cross the shortest unit on the map of the stars. Let those numbers blur now, because the point of this chapter was never the numbers themselves. The point is the shape of what we just watched. We multiplied our speed by 20, then by 10, then doubled it, then tripled it again, climbing from a stroll to hypersonic flight, an improvement of more than 1,000 times over walking, and the journey shrank from 200 million years to 150,000. Real progress, genuinely earned, and still hopelessly outmatched. And here is the deeper truth of this rung. The thing worth carrying up the ladder with us. Every machine in this chapter, every car and jetliner and record-breaking rocket plane was built to travel through air, against gravity, near the surface of a world. They are masterpieces of the sky, and the sky is exactly what limits them. An engine that breathes air cannot run where there is no air. A wing is useless where there is nothing to press against. Wheels need roads, and there are no roads. The space between the stars offers no runway, no fuel stop, and no wind. To go meaningfully faster, we cannot simply build a better airplane. We have to leave the sky behind entirely. If your eyes are heavy, let them close. You will not miss anything that matters. The next rung of the ladder rises above the atmosphere itself, to the machines that ride fire instead of wings, and to the fastest any human being has ever moved. There is a number that guards the door between the Earth and everything else. And it deserves a slow introduction. To leave our planet entirely. To break free of its gravity and never fall back. A vehicle must reach about 25,000 miles per hour. Engineers call this escape velocity. It is not a rule anyone wrote or a law anyone passed. It is simply the price of admission that gravity charges. The same for a pebble as for a palace. And for almost all of human history, it might as well have been infinite. No wing can reach it. Because wings need air. And the air gives out long before that speed arrives. The only machine that has ever paid the price is the rocket. And a rocket works on the strangest and simplest idea in all of transportation. It carries everything it needs along with it. And it moves forward by throwing part of itself backward. As fire, as fast as chemistry will allow. Picture the machine that paid that price most famously. The Saturn V, the rocket that carried the Apollo astronauts toward the moon, stood taller than the Statue of Liberty. On the launch pad, it weighed about as much as a naval ship, and nearly all of that weight, more than 90% of it, was fuel, not crew, not cargo, not instruments. Full. The astronauts rode in a small capsule at the very top, in a space roughly the size of a car's interior, perched on a tower of contained fire. When the 5 great engines of the first stage lit, they drank propellant at a rate almost impossible to picture, emptying the equivalent of 3 backyard swimming pools in the dozen seconds it took the rocket simply to clear its own launch tower. And it needed every drop, because the door out of the sky is heavy, and chemistry has only so much strength in its arms. And it worked. In May of 1969, the crew of Apollo 10, 3 astronauts named Thomas Stafford, John Young, and Eugene Cernan, flew a full rehearsal of the moon landing. And on the way home, their capsule fell back toward Earth faster than any human beings have ever traveled, before or since. According to NASA's records, they reached nearly 25,000 miles per hour as they returned through the atmosphere toward the Pacific Ocean. More than half a century has passed, and that number still stands as the all-time speed record for our species. 3 men, 1 spring evening, and no one has ever gone faster. Now, to be fair to the physics, that record was a brief peak, the speed of a long fall from the moon, not a pace their capsule could hold on an open road. But this is a night for thought experiments. So let us grant the impossible. If that record speed could somehow be held steadily, in a straight line pointed at the stars, we can ask the question of the night. At this speed, the fastest any human has ever moved, how long would it take to cross 1 light year, roughly 27,000 years? Feel the strangeness of that answer for a moment. 27,000 years is, at last, a number with a fully human shape. It is no longer the age of dinosaurs or the drift of continents. 27,000 years ago, there were people exactly like us, with families and languages and firelight, wrapping themselves in furs against the cold of the Ice Age, painting horses and bison on cave walls in what is now France and Spain. If one of those artists had climbed aboard an Apollo capsule on the night the paintings were finished, and had flown toward the stars at record speed ever since, they would just now be arriving at the 1 light year mark. While down here on Earth, astonishingly, their paintings still cling to the stone, preserved in the dark, waiting for flashlights. Notice something else. something quiet and important: the moon, the destination that defined a generation, that demanded the largest machine ever built, and the daily efforts of some 400,000 people, sits about 250,000 miles away. 1 light year is roughly 24 million times farther. The entire Apollo program, the grandest voyage our species has ever completed, covered about 1/24 millionth of tonight's distance, and yet no one who watched those launches felt small. They felt enormous. Hold on to that, because it is the real heart of this whole night. The size of the journey has never once determined the size of the meaning. Let your breathing slow here, and let the Ice Age painters return to their firelight, because a fair question has probably already formed somewhere in your drifting thoughts. The Apollo capsule carried people, and people are heavy, and keeping people alive is heavier still. All that air and water and food and shielding, all of it fighting the arithmetic of the fuel tank. What if we did not send people at all? What if we sent only a machine, small and tireless and uncomplaining, and let it use every clever trick that gravity allows? How fast could such a machine go? That question has an answer, and the answer is not a thought experiment. It is a real machine, flying right now, tonight, closer to a star than anything our species has ever built. The fastest thing our species has ever built does not look fast. It looks like a patient little machine hiding behind a shield, roughly the size of a small car. And its great secret is this: it did not earn its speed by pushing harder than everything that came before it. It earned its speed by falling, deliberately and brilliantly, toward the most massive object in our solar system. The machine is called the Parker Solar Probe, and NASA launched it in August of 2018 with a mission unlike any flown before. Its job is to study the sun up close, to fly again and again through the sun's outer atmosphere, a region of heat and chaos no spacecraft had ever dared to touch, protected by a heat shield facing temperatures far beyond anything on any launch pad. The probe was named for a physicist called Eugene Parker, who, in the 1950s, predicted the existence of the solar wind, the constant river of particles flowing outward from the sun, back when many of his colleagues doubted any such thing could be real. He was a young researcher then. His paper was initially rejected, and he turned out to be right. He lived to see the launch, the first time NASA ever named a spacecraft after a living person, and he watched his namesake rise on a pillar of fire. Bound for the star he had spent his life explaining. He died a few years later. Having seen his own name on its way to the sun, here is where the story becomes a lesson in how the universe actually hands out speed. A rocket alone could never have made this probe the fastest object in history, because chemistry, as we saw on the last rung, has limited strength in its arms. So the mission's designers borrowed strength from the solar system itself. They aimed the probe past the planet Venus, again and again over the years, using each flyby to bend its path and shed momentum, letting it drop closer to the sun with every orbit, like a stone circling a drain in the slowest possible motion. And each time the probe swings around the sun, it does what every falling object does. It speeds up. The sun's immense gravity hauls it inward and slings it through the lowest point of its orbit at a pace no engine could ever have provided. In a very real sense, the probe is no longer being pushed by us at all. It is falling, over and over, with exquisite precision, and simply refusing to hit anything. In December of 2024, on one of its closest passes, the Parker Solar Probe swept within about 3.8 million miles of the solar surface, flying through material at temperatures that would erase most machines. And, according to NASA and the mission team at the Johns Hopkins Applied Physics Laboratory, it reached a speed of roughly 430,000 miles per hour. 430,000 miles per hour. At that pace, you could fly from New York to Tokyo in under a minute. You could cover the distance from the Earth to the Moon, the crossing that took the Apollo crews 3 days, in about half an hour. It is 17 times faster than the fastest humans have ever flown. It is, by an enormous margin, the fastest object human hands have ever made. So, here we are again. At the question, we carry up every rung of this ladder. That top speed, like Apollo's, is a brief peak, held only in the deepest part of the fall. So, once more, we grant the impossible. If the probe could somehow keep that record pace on a straight road to the stars, at this speed, how long to cross 1 light year? About 1,500 years. Let that arrive slowly, because it is the most double-edged number of the night so far. 1,500 years is astonishing progress. On the first rung of this ladder, the walk took more than 200 million years. We have shortened the journey by a factor of more than 100,000 since then. And 1,500 years is a length of time the human mind can genuinely hold. 1,500 years ago, the Western Roman Empire had recently fallen. There were kingdoms and monasteries and trade roads, grandmothers telling stories by lamplight, children asking what the stars were. If the Parker Solar Probe had launched then into the world of early medieval Europe and held its record speed ever since, it would just now be finishing the first light year of its trip. But now feel the other edge. 1,500 years is roughly 60 human generations. 60 successive lifetimes of engineers keeping faith with a machine none of them launched and none of them would see arrive. And that speed, remember, was never truly the probe's own. It was borrowed from the sun. The probe only moves that fast because it is falling around a star, held close on a leash of gravity. The moment such a machine tried to leave the sun behind and strike out toward another star, it would have to climb back out of that same gravity, paying back most of the speed it borrowed. The way a ball thrown upward pays back its rise. The fastest object we have ever built is fast the way a diver is fast, magnificent on the way down, and never taking that speed home. So, the lesson of this rung is a strange one. Falling has taken us further than fire. Gravity, the very force that locked our species to the ground for 100,000 years, turned out to be a resource, something that could be cleverly spent. But gravity's gifts are loans, not wages, and the space between the stars is flat and empty, with no massive suns conveniently placed along the road to fall around. Out there, a traveler keeps only the speed it truly owns, which raises the question your drowsy mind may already be reaching for. Is anything we have built actually out there, in that flat and empty dark, moving under no power at all, keeping only the speed it owns, genuinely and permanently on its way out? Not a thought experiment, not a borrowed peak, a real machine, with a real launch date, flying right now while you rest, carrying something unbearably human on its hull. There are such machines, a small family of them. In fact, But two of them are sisters. They are older than most of the people listening tonight. And they are the only two still speaking to us from beyond the edge of the sun's realm. In the late summer of 1977, in the span of just 16 days, two nearly identical spacecraft left the Earth from Cape Canaveral in Florida. They were called Voyager 1 and Voyager 2. And tonight, while you rest, they are the farthest human-made objects in existence, still flying, still faintly whispering home, nearly half a century after their launch. They are not the only machines our species has set on escape paths from the Sun. Two earlier probes, named Pioneer 10 and Pioneer 11, are also drifting outward, silent now for decades. And a younger spacecraft, called New Horizons, is following its own road out after visiting Pluto. But the Voyagers flew farthest and lasted longest. And they are the only two still calling back to us from interstellar space. If tonight's question has a real-world answer, these two sisters are it. Their story begins with a rare piece of cosmic luck. In the 1960s, a young engineer at NASA's Jet Propulsion Laboratory named Gary Flandreau was assigned to study future missions to the outer planets. And while working through the orbital charts, he noticed something remarkable. Jupiter, Saturn, Uranus, and Neptune were slowly drifting into an alignment that occurs roughly once every 176 years. A spacecraft launched at just the right moment could visit them all, one after another, using each planet's gravity as a stepping stone, stealing a little momentum from each world to fling itself onward to the next. The previous time the planets had offered this arrangement, Thomas Jefferson was President of the United States, and the fastest vehicle on Earth was a sailing ship. The engineers of the 1970s understood they were holding a once-in-many-lifetimes invitation, and they took it. So the sisters flew, and what a flight it was. They swept past Jupiter and photographed its storms in detail no telescope had ever managed. And they discovered volcanoes actively erupting on its moon Io, the first active volcanoes ever seen anywhere beyond Earth. They revealed Saturn's rings as thousands of delicate ringlets and found moons no one knew existed. Then Voyager 2 flew on alone to Uranus and to Neptune. And it remains, to this night, the only spacecraft ever to visit those two blue worlds. The first close-up portraits that defined those planets for a generation, the pale turquoise of Uranus, the deep stormy blue of Neptune with its racing white clouds, came from this one machine. A machine carrying less memory than a single photograph on your phone, working flawlessly at the far edge of the map, its signals taking hours to crawl home at the speed of light. And when the planetary tour was over, the most important part of the journey quietly began, because all those gravitational stepping stones had given the Voyagers something almost nothing we build ever receives. Enough speed to leave forever, not to orbit, not to fall back, to leave. Their outward speed is a true escape speed. And though the sun's gravity still tugs at them and will slow them gradually for ages to come, it can never reclaim them. They will coast outward for timescales far beyond any human history. In 2012, according to NASA, Voyager 1 crossed the boundary where the sun's wind gives way to the thin breath between the stars, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Tonight, Voyager 1 is more than 15 billion miles from home, so far away that its radio whisper, traveling at the speed of light, needs nearly a full day to reach the great antennas still listening for it on Earth. The power in that whisper, by the time it arrives, is billions of times fainter than the battery in a wristwatch, and still we hear it. Now, at last, we can ask tonight's question of a machine that is genuinely making the trip. Voyager 1 is traveling at about 38,000 miles per hour, and unlike the Parker probe's borrowed peak, this is a lasting pace, a speed it will very nearly keep for the rest of time. So, at this speed, how long to cross 1 light year? About 17,500 years. There it is. After all the rungs of this ladder, that is the real number. The true answer for the fastest travelers we have ever actually sent. 17,500 years for 1 light year. Voyager 1. Launched before most of the people hearing these words were born, has in all its decades of flight covered roughly 0.25% of a single light year. And the nearest star system, Alpha Centauri, sits more than 4 light years away, though neither Voyager is even pointed toward it. The sisters are headed into the general dark, and NASA's navigators calculate that in about 40,000 years, Voyager 1 will pass within a couple of light years of a small star called Gliese 445. That distant, glancing drift past a star it will never touch is the closest thing to an arrival its endless journey contains. But the Voyagers carry something that changes how that number feels. Bolted to the side of each spacecraft is a golden phonograph record. Conceived by a team led by the astronomer Carl Sagan. On it are greetings in dozens of human languages, the sounds of surf and rain and birdsong, the cry of a newborn baby, music from across our cultures, from Bach to Beethoven to Chuck Berry. On it is the sound of a human heartbeat, and on it, recorded as electrical impulses, are the brain waves of a young woman named Anne Druyan, captured during an hour in which, by her own account, she thought about history, about civilization, and about the man she had just fallen in love with, the project's own leader, Carl Sagan, whom she would later marry. The record was never really meant for aliens. Its makers knew the odds of anyone ever finding it were vanishingly small. 2 tiny objects in an ocean of night. It was meant for us. It was a way of saying that a species which cannot yet cross the distance can still reach into it and leave something tender there, drifting at 17,000 years per light year, addressed to no one, signed by everyone. Let the sisters fly on now, without you for a while. They are very good at continuing. Somewhere in the cold beyond the planets, 2 gold-plated records are being carried through the silence, unplayed, uncracked, holding a woman's thoughts about love and a baby's first cry, in a quiet so complete that nothing has ever heard them at all. This chapter is a resting place. There will be no new machines in it, no launches, no speeds to compare. We have earned our number. 17,500 years for 1 light year at Voyager speed. And now we are going to give it a shape. For the next few minutes, we will walk backward through those years, the way you might walk back through an old family album, page by page, and see what such a span actually contains. If your eyes are closed, keep them closed. This chapter asks nothing of them. Begin by stepping back 500 years. The year is roughly 1526. There are ships crossing oceans under sail, printed books spreading across Europe, painters at work on ceilings in Italy. This is deep history, the kind wrapped in museum glass. And yet notice, we have spent only 1/35 of our journey backward, the entire age of exploration, of printing presses and telescopes, and every scientific idea we have met tonight, fits into a thin sliver at the very near edge of Voyager's light year. Step back 2,000 years. Rome rules the Mediterranean world. A traveler can walk on paved roads from Spain to Syria, sleeping at inns along the way. And the pyramids of Egypt are already ancient, already tourist attractions, older to the Romans than the Romans are to us. And still, we have covered barely a tenth of the distance back. Step back 5,000 years. And now, writing itself is brand new. The first symbols pressed into wet clay in Mesopotamia. The very beginning of anything any historian can read. Everything that has ever been written down. Every letter. Every law. Every recipe. Every love poem. Every book in every library on Earth. All of it lives inside the most recent 5,000 years. And our walk backward through Voyager's single light year is not yet a third complete. Keep going, 10,000 years back, and we arrive near the dawn of agriculture, when permanent farming villages were only beginning to reshape human life. When someone first saved seeds through a winter on purpose and planted them in the spring. The quiet revolution that made every city and every nation possible. Before this, essentially everyone who ever lived was a wanderer. And still we walk. Another 5,000 years down. Another 2,500 beyond that. Until at last, 17,500 years ago, we arrive at the far end of Voyager's single light year. And what do we find there? We find a world still deep in the last great ice age. The coldest peak of that age had recently begun to pass, but vast sheets of ice, in places more than a mile thick, still lay across Canada and northern Europe. And so much of Earth's water was locked up in that ice that the oceans sat hundreds of feet lower than they do tonight. Lands now drowned beneath the sea were open ground under the wind, and there were footprints on them. Because there were people, this is the part to hold closely. Fully human people, with families and languages and firelight, with humour and grief and music. Alive at both ends of this journey, in caves scattered across what is now France and Spain. Around this time, some of them were painting herds of horses and bison on stone walls by the light of small flickering lamps. The work is so accomplished that when a cave in northern Spain called Altamira was first shown to the scientific world in the 1800s, many experts refused to believe it. The paintings were simply too good. They said, too alive, to have been made by people so long ago. They were wrong. And the paintings are still there. If one of those painters had watched a Voyager leave Earth on the night the last of them dried, the spacecraft would be completing its first light year just about now, while the paint, against all odds, still clings to the rock. That is 1 light year, at the speed of the fastest travelers we have ever launched. Not the age of dinosaurs, not the drift of continents, the whole of human civilization, from the ice to this evening, with room to spare, every city ever built, every language ever spoken, every person who ever fell asleep to a story being told in the dark. All of it fits inside the crossing. Now, here is the question this resting place exists to ask. And there is no need to answer it tonight. Is that number a defeat? It is tempting to hear 17,000 years and feel small. To conclude that the stars are simply not for us, that the universe built its rooms too large for its tenants. But consider what we just walked through. At the far end of that span, our entire species owned nothing but stone, fire, and patience. No wheeled transport, no writing, no worked metal, and, in the time it takes Voyager to cross 1 light year, we went from painting animals by lamplight to building the Voyagers themselves. The distance did not shrink tonight. We grew, and no law of nature says we are finished growing. A species that crossed the gap from cave walls to interstellar spacecraft within a single light year of travel time has no business assuming its current speed is its final speed. That thought is the hinge of the whole night. So let it rest in you without any pressure. Everything below this rung of the ladder was the story of how fast we are. Everything above it is the story of how fast we might become. Up there, wait the sails pushed by light, the engines designed to burn atoms instead of kerosene, the blueprints with names like Orion and Daedalus, drawn in complete seriousness by people doing careful arithmetic about journeys no one alive will take. But before we can climb to any of it, we have to stop and face something. Because there is a reason rockets stalled where they did. A reason Apollo and Voyager sit within shouting distance of each other despite decades of trying. It is not a failure of nerve or funding or imagination. It is a wall, an actual mathematical wall, discovered more than a century ago by a nearly deaf schoolteacher working alone in a log house in rural Russia. Before we dream upward, we owe it to the dream to understand the wall. Far from any city, in the Russian countryside, at the close of the 19th century, there was a log house on a hill above a river, and in it lived a schoolteacher the neighbors considered strange. His name was Konstantin Tsiolkovsky. Scarlet fever in childhood had taken most of his hearing, and with it, any ordinary path through school. He was sent home, essentially dismissed from the world of other children, and by his own later account, those years of silence pushed him inward, toward books and toward machines. As a teenager, he was sent to Moscow to educate himself, where he lived on very little, reportedly on black bread and not much else, and spent his days in the public library working through mathematics and physics, book by book, alone, teaching himself in silence what other young men were being taught aloud. He returned to the provinces, became a teacher of arithmetic in a small town, and there he stayed for the rest of his working life. By day he taught children their sums. By night, in that log house, surrounded by homemade models and instruments he built with his own hands, he thought with unusual discipline about a subject almost no serious person on Earth was thinking about at all. He thought about how human beings might leave this planet. He was doing this decades before anyone had flown an airplane. He had no laboratory, no funding, no colleagues, and very little hearing. What he had was arithmetic, and a certain immunity to being laughed at. He worked out that a rocket, unlike every other vehicle, could function in a vacuum because it does not push against anything outside itself. He sketched multi-stage rockets, and rockets fueled by liquid oxygen, and stations turning in orbit to make artificial gravity, all of it while the fastest thing his neighbors had ever seen was a train, and in the year 1903, the very same year, the Wright brothers first staggered into the air above the sand at Kitty Hawk. This self-taught, nearly deaf schoolteacher published an equation that still governs every rocket that has ever launched. From the smallest sounding rocket to the Saturn V, 2 continents apart, in the same 12 months, one pair of brothers proved a machine could leave the ground, and one man alone worked out the mathematics of leaving the world. Neither knew the other existed. Engineers today call his result simply the rocket equation. Some of them, less formally, call it the tyranny of the rocket equation. And by the end of this chapter, you will see why the word tyranny is fair. Here is the heart of it. With no mathematics required, a rocket moves by throwing part of itself backward. That is the whole trick. Fire goes one way, rocket goes the other, which means a rocket must carry from the very first second of its flight every ounce of the propellant it will ever use. There are no fuel stations on the way up, and this creates a trap that feels almost like a riddle. If you want to go faster, you need more fuel, but that extra fuel has weight. So, now the rocket is heavier, which means you need even more fuel just to push the fuel you added, which makes the rocket heavier still, which demands more fuel again. Tsiolkovsky's equation describes exactly how this spiral unfolds, and its verdict is merciless. The fuel required does not grow gently, in step with your ambitions. It grows exponentially. Every additional gain in speed costs vastly more than the one before it. Doubling your target speed does not double the fuel. It can square the whole scale of the problem. Let the shape of that sink in slowly, because it quietly explains everything we have seen tonight. It explains why the Saturn V, a machine as tall as a skyscraper, was more than 90% fuel, nearly all of it gone within minutes, just to send a capsule the size of a car toward the moon. It explains why, in half a century of brilliant engineering since Apollo, chemical rockets have never pushed a spacecraft dramatically beyond the speeds the Voyagers achieved. The easy gains were taken long ago, and the gains that remain sit on the steep part of the curve, where each small improvement demands absurd new tonnages of propellant. Engineers do not fail to build faster rockets because they lack imagination. They fail because the arithmetic bills them for a fuel tank the size of a mountain, and then, if they persist, the size of a moon. But let us be careful and exact here, because this is the most misunderstood point of the entire night, and getting it right matters more than making it dramatic. The rocket equation does not forbid a chemical rocket from ever reaching 1 light year. It cannot. The proof is already flying. The Voyagers were launched by chemical rockets, and given 17,500 years. Voyager 1 will indeed cross that distance, quietly, at the speed it already has. Chemistry can absolutely begin an interstellar journey. What chemistry cannot do is make that journey short. To reach even a modest fraction of the speed of light with a chemical rocket, the equation begins asking for propellant in quantities that abandon all sense. Tanks with the mass of worlds, all to move one small payload. So the wall in front of us is not a wall against going. It is a wall against going quickly. And for a species with lifetimes as brief as ours, those two walls feel almost the same. There is something oddly soothing in finally seeing the true shape of a problem. the way it can be a relief to understand why a stubborn door will not open. Even before you know another way in, the door was never stuck. It was locked, and chemistry was simply the wrong key. And no amount of pushing harder on the wrong key has ever opened anything, and nobody understood this more clearly, or took it more calmly, than Tsiolkovsky himself. 100 years ahead of tonight. He never believed chemical rockets were the final word. He treated them as the first rung of a taller ladder, filling notebooks with what would come after, sketching the far future in a small town where nobody could hear him say it. Recognition came to him late, only in the last years of a long life, and much of what he predicted arrived decades after his death, in a century he never saw. He left behind a sentence that has been quoted by every generation of space dreamers since. And it is worth hearing slowly, in the dark. At the exact middle of our journey, Earth is the cradle of humanity. He wrote, but one cannot live in a cradle forever. So hold the lesson of this chapter, because it is the turning point of the entire night. The tyranny of the rocket equation rules every vehicle that carries its own propellant. Every number in that merciless spiral, every tank the size of a mountain, applies only to a ship that must bring its push along for the ride, which invites a question so simple it sounds like a child asking it. The very kind of question this whole night began with: what if the push stayed home? What if a ship carried no fuel at all, and the force that drove it came from somewhere else? From behind, from far away, from an engine that never had to leave the ground, or an engine that was never built by anyone at all. It sounds like a trick. It is not. The universe has quietly allowed this loophole all along, and the proof of it has been resting on your face every clear afternoon of your life. Here is a fact that sounds like poetry but is measured physics. Light pushes. Every beam of light that strikes a surface gives it a nudge. Unimaginably small, but real. Sunlight is pressing on your window right now. It pressed on your face the last time you stood outside on a clear day, with a force so faint that all the sunlight falling on an entire football field pushes, all together, with roughly the weight of a single coin. That is the whole budget. One coin of force, spread across a field of grass. For all of human history, that whisper of pressure went completely unnoticed, and it is easy to see why. On Earth, drowned out by wind and friction and gravity. A push that faint changes nothing at all, but away from a planet, things are different. Deep space offers almost no drag, no road resistance, none of the thick atmosphere that steals speed from every vehicle down here. And in near emptiness, even a faint push can keep accumulating, for as long as the light continues to act, because there is almost nothing to erase what has already been gained. Second after second, hour after hour, month after month, the whisper adds up. A force too weak to move a leaf on Earth can, given enough patience in the dark, carry a ship to speeds a rocket would envy. And in that fact lies the loophole in Tsiolkovsky's Tyranny, the answer to the question we carried out of the last chapter. A ship pushed by light needs no fuel tank, because the light is not made on board. The engine can be 93 million miles away, burning for free, with no intention of ever stopping. The engine can be the sun. The idea is older than you might guess. 400 years ago, the astronomer Johannes Kepler noticed that the tails of comets always stream away from the sun, no matter which direction the comet itself is traveling, as if some invisible breeze were blowing outward from the fire at the center of everything. In a letter to Galileo, he wondered whether ships might one day be built to catch heavenly breezes, the way sails catch the wind at sea. He was wrong about the details, as anyone would have been. We now know that comet tails are shaped by both the pressure of sunlight and a genuine wind of particles streaming from the sun. Two effects Kepler had no way to separate or even name, but the image he reached for, of sails driven by something pouring out of a star, turned out to be one of the most durable intuitions in the history of space travel. In the 20th century, engineers gave it a shape and a name: the solar sail. Build a mirror, they said, vast and impossibly thin, thinner than a soap bubble, lighter than the box it shipped in. Unfold it out there, angle it toward the sun, and let the light itself lean against it. For free, for as long as you like. For decades, the solar sail stayed a beautiful drawing, and it kept failing to leave the page. Early attempts were lost when their launch rockets failed. Funding came and went. The idea began to seem like one of those dreams that is permanently 20 years away. And then, in 2010, it finally flew. The Japanese Space Agency, JAXA, launched a small spacecraft called Icaros, a square sail about 14 meters on a side and thinner than a human hair, which unfurled in deep space on its way toward Venus and became the first vehicle in history to be measurably pushed through interplanetary space by sunlight. The push was tiny, exactly as the physics promised, but it was there, plain in the tracking data, undeniable. Humanity had built a ship with no fuel, and the sun was moving it. 9 years later came a smaller, scrappier triumph. A non-profit organization called the Planetary Society, funded not by any government but by tens of thousands of ordinary space enthusiasts around the world, flew a little spacecraft called LightSail 2 in orbit around the Earth. Unfurled. Its sail was about the size of a boxing ring, made of mirrored material thinner than a trash bag. According to the mission's published results, it used sunlight as its only source of propulsive thrust, measurably raising one side of its orbit with nothing but the pressure of light, even while the thin upper atmosphere kept tugging at it from below and slowly wearing the orbit down. That detail matters, and the team said so plainly. Near a planet, a sail is always sailing into a headwind. The remarkable thing is that it sailed anyway, and the people who paid for that ship were not generals or billionaires. They were teachers and nurses and retirees who simply wanted to see a sail fly. It flew above their heads for years, a mirror in the sky, pushed by the same sunlight that was warming their gardens. Now, let us be clear-eyed about what solar sails can and cannot do. Sunlight weakens quickly as you travel outward, spreading and thinning with distance. By the time a sail reached the orbits of the outer planets, the sun's push would have faded to almost nothing, and from there the sail would simply coast, keeping whatever it had already gained. A ship riding sunlight alone would not dramatically beat the voyagers to the 1 light-year mark. Sunlight is a harbour breeze. It is perfect for setting out, gentle and free and everywhere, and far too soft for the open ocean between the stars. And yet feel what has actually changed on this rung of the ladder, because it is the largest change of the night. Every vehicle below this rung, every car, every jet, every rocket Every falling probe obeyed the same iron rule. The push had to ride along, and the push was heavy. The sail is the first vehicle we have ever flown where the push stays home. The tyranny of the fuel tank simply does not apply to it. And the moment the push stays home, a new question opens like a door left ajar. If a gentle, natural light can move a ship, what could a fierce, artificial light do? What if, instead of waiting for the sun's soft breeze, we built the wind ourselves, aimed it, and turned it up as far as our machines allow? What if we pointed the most powerful array of lasers ever constructed at a sail the size of your hand and pushed it, deliberately, toward another star? That is not a fantasy drifting past at the edge of a dream. It is a real research program, announced by real physicists, with published studies and a named target star. Its stated ambition is to cross distances like tonight's knot in 17,000 years. But within the span of an ordinary career, in April of 2016, at the top of a skyscraper in New York City, a small group of people stepped up to a podium and announced one of the boldest engineering ideas ever proposed in public. The physicist Stephen Hawking was there. Beside him stood a technology investor named Yuri Milner, who had been named after the first human to fly in space, who had grown up in Moscow dreaming about the stars, and who was now pledging $100 million of his own money to fund the research. The project they announced was called Breakthrough Starshot. Its stated goal sounded, at first hearing, like something that had escaped from a bedtime story. They proposed to send spacecraft to Alpha Centauri, the nearest star system, more than 4 light-years away, and to do it not in 17,000 years, but in roughly 20 years. After everything we have climbed through tonight, you can feel how outrageous that number is. So let us take the idea apart slowly, piece by piece, and see how serious people intend to keep such a promise. Then, let us be equally serious about everything standing in their way. The first move is the one we learned on the last rung. The push stays home. Starshot begins with a sail, but it abandons the sun's soft breeze entirely. In its place, the plan calls for an enormous array of lasers on the surface of the Earth, most likely in a high, dry desert where the air is thin and still. Not one giant laser, but millions of small emitters spread across a site perhaps a kilometer wide, all locked together with exquisite precision so that their separate beams combine into a single column of light. The combined power called for in the project's studies is about 100 gigawatts, comparable to the output of dozens of large power plants, focused for a few crucial minutes on one tiny object rising into the sky. The second move is just as radical. The ship must be almost nothing. This is where Starshot breaks with every spacecraft ever flown. The Voyagers weigh about as much as a small car. The Starshot craft, called a Starship in the project's papers, would weigh about a gram. A single gram, roughly the weight of a paperclip. An entire spacecraft printed onto a wafer, carrying miniature cameras, sensors, a power source, and a tiny transmitter attached to a sail a few meters across and only a few hundred atoms thick. The whole vehicle, sail and all, could rest on your open palm, and you would barely feel it there. That lightness is not a compromise. It is the entire secret. When the Great Laser Array fires at something so small and so light, the acceleration is ferocious. Tens of thousands of times the force of gravity, a violence no human body could survive, and no human body will ever need to. In a matter of minutes, the little craft would be flung to the project's target speed. 20% of the speed of light. 20% of the speed of light. Place that on tonight's ladder and feel where it lands. At that pace, the question we have asked on every rung finally collapses into something almost casual. At this speed, how long to cross 1 light year? 5 years. Not 17,500. 5. A crossing that swallows the whole of human civilization at Voyager speed becomes, for this paperclip of a starship, about the time it takes a child to go from being born to starting school, and Alpha Centauri itself, the actual target, would lie some 20 years of flight away, close enough that scientists who watched the launch could still be at their desks when the first pictures arrived. Pictures that would then need another 4 years and a few months to cross back to Earth at the speed of light. Now, the other side of it. Because everything I have just described exists on paper. Breakthrough Starshot is a research program, not a countdown. No Starship exists tonight. No laser array exists tonight. What exists are studies, prototypes of individual components, and a long, publicly acknowledged list of unsolved problems. The project's own scientists have never hidden that list. Avi Loeb of Harvard chaired its advisory committee. Pete Worden, a former director of a NASA research center, leads the initiative. Both have spoken openly about how much remains unsolved. Consider the sail. It must reflect the beam almost perfectly. Absorbing even a small fraction of 100 gigawatts would vaporize it in an instant. No material yet manufactured has fully proven itself for that job. Consider the beam. It must stay locked on a target a few meters wide, through the shimmer and boil of Earth's atmosphere, while that target accelerates away at thousands of miles per second. Consider the 20-year cruise. Interstellar space is not empty, and at a fifth of the speed of light, even microscopic grains of dust could pit the sail, burn small holes through it, or damage delicate components, while a larger grain could end the mission outright. A sail, a few hundred atoms thick, has very little to spare. Consider the homecoming. A transmitter weighing less than a coin must somehow whisper its findings across more than 4 light years. A signal so faint that catching it may require a receiving system of comparable scale to the great laser itself. An enormous eye built for no purpose but to see a firefly blink from another star system. Some published estimates put the full cost near that of the largest scientific projects ever funded. With decades of engineering standing between tonight and any launch, some scientists believe a version of Starshot could fly within our lifetimes. Others believe the idea has arrived a century early. Nobody yet knows which of them is right, and anyone claiming certainty in either direction has left the evidence behind. And yet this rung feels different from every rung below it, and it is worth understanding exactly why. No single element of the basic concept obviously violates established physics. Light pressure is real and measured. Gram-scale electronics are in your pocket tonight. Arrays of small emitters combining into one great beam are proven technology at radio wavelengths. Whether all of those elements can be made to work together at the required scale, at a survivable cost, is genuinely unknown. And unknown deserves respect as a word. But compare it to the war we met a few chapters ago. Below this rung, the limit was built into the architecture itself. A vehicle that carries its own push is billed by the rocket equation, no matter how clever the engineers are, no matter how large the budget grows. Here, the architecture changes. The push stays home. The payload becomes almost nothing. And the questions that remain are questions about materials, precision, money, and will, questions that do not yet have answers, but that are permitted by the laws of nature as we currently understand them to have answers. That is not a promise that the little sail will ever fly. It is something rarer in this story. It is permission, so let the sail go for now, glittering in its column of light, somewhere in a possible future. A paperclip is a wonderful scout, and it is also almost nothing. It can carry no passengers, no cargo, no life. Its entire genius is its emptiness, which leaves the older dream untouched and waiting. What could push real weight toward the stars? Laboratories, supplies, shielding. Someday, perhaps people. For that you need the most powerful thing our species has ever laid hands on. And we have had it since the middle of the last century, filed away in folders that once carried the word secret. Somewhere in the archives of the 20th century, there are blueprints for starships, not sketches by dreamers, not illustrations for magazine covers, but engineering studies, with mass budgets and trajectory tables and cost estimates, drawn up by some of the most serious physicists of their era. None of them were ever built, but none of them were ever quite disproven either. And that distinction between the unbuilt and the impossible is the quiet thrill of this entire chapter. The story begins in the late 1950s, in the strangest season of the atomic age. Humanity had just learned to release the energy bound inside the atomic nucleus. And that energy dwarfed chemistry, the way an ocean dwarfs a raindrop, pound for pound. Nuclear fuel holds millions of times more energy than the kerosene and oxygen that lifted the Saturn V. To a certain kind of mind, the conclusion was irresistible. Chemical rockets were rowboats. The atom was the wind. And at a laboratory in San Diego, a team that included the physicist Freeman Dyson, one of the most original scientific thinkers of his century, began designing a ship to catch that wind. The effort was called Project Orion, and its method, described plainly, still sounds like something you should not be allowed to say out loud. The Orion ship would fly by riding controlled atomic explosions. Small nuclear charges would be released from the rear of the vehicle, one after another, and detonated at a carefully calculated distance behind it. Each blast would slam into an enormous armored disc at the ship's stern, called a pusher plate, mounted on shock absorbers the size of buildings, and each shove would drive the ship forward. Explosion after explosion, shove after shove, thousands of times in sequence. The vessel would climb to speeds no chemical rocket could approach. The physicists checked the numbers again and again, expecting to find the fatal flaw. And the numbers kept holding. Many of the required materials and principles were known, and the energy source was real. Dyson's studies imagined ships the size of ocean liners, carrying not grams of payload, but thousands of tons. and versions of the concept pushed to their limits pointed towards speeds of a few percent of the speed of light. Dyson wrote seriously about star voyages lasting a century or two, ships carrying whole communities, arriving at another sun with the grandchildren of the crew that departed. Orion was never built, and the reasons deserve to be said plainly, because they are reasons we can be glad about. A ship that rises from Earth on a chain of atomic explosions scatters radioactive fallout into the atmosphere with every launch. In 1963, the nations of the world signed a treaty banning nuclear detonations in the atmosphere and in space. The treaty was written to restrain weapons, and the world is better for it. It also, almost as a side effect, closed the folder on Orion. Dyson accepted the trade with open eyes, and by many accounts carried a certain wistfulness about it for the rest of his long life. The ship in the filing cabinet had asked a price the Earth was not willing to pay, and the Earth, quite reasonably, declined to pay it. The folder did not stay closed for long, because a generation later, engineers found a cleaner way to ask the atom for help. In the 1970s, members of the British Interplanetary Society, the oldest space advocacy organization in the world, gave themselves a strict assignment: design an uncrewed starship using only physics already understood, aim it at a real star, and follow the arithmetic wherever it leads. With no miracles permitted anywhere in the design, they worked on it for 5 years, meeting in the evenings, mostly unpaid, and they called it Project Daedalus. The ship they drew was colossal, longer than a football field and assembled in orbit, and its engine used not atomic explosions, but fusion, the same process that powers the sun. Tiny pellets of fusion fuel would be injected into a reaction chamber and ignited by beams of electrons. 250 pellets every second. Each one a miniature star flaring for an instant inside a throat of magnetic fields. And the ship would ride that flickering fire for years. Burning this way, Daedalus was calculated to reach roughly 12% of the speed of light. At this speed, how long to cross 1 light year? About 8 years. The study aimed the ship at Barnard's star, about 6 light years away. A one-way flight of roughly half a century, short enough to fit inside a single scientific career. And here the arithmetic must be given its full weight. Because paper conceals mountains, Daedalus called for a rare form of helium, called helium-3, so scarce on Earth that the study proposed harvesting it from the atmosphere of Jupiter with floating robotic factories, an enterprise that would by itself dwarf anything humanity has ever attempted. The pulsed fusion engine at the heart of the design has never been built at any scale, not even in a laboratory. The ship would need to run itself, flawlessly, for decades, with no possibility of repair, farther from help than anything has ever been. So it will not do to say, as some summaries breezily do, that Daedalus was merely too expensive. Nothing in the concept obviously breaks known physics, but nearly every major system in it lies beyond demonstrated engineering, and far beyond any budget any civilization has yet committed to the stars. Later groups, including a modern successor study called Project Icarus, have revisited and refined the design, and after 50 years, the verdict has stayed roughly the same. The road is not forbidden. It is simply unbuilt, from the first mile to the last. So, what do these old folders actually give us? Not a vehicle we can board, something quieter, and in its way more valuable. They are proof of scale, proof that the gap between us and the stars is measured in decades of committed effort, oceans of treasure, and engineering not yet demonstrated, rather than in flat impossibility, the tyranny of the fuel tank, which ruled every rung of the lower ladder, bends before the atom. It does not vanish, but it bends, enough to bring 1 light year down from 17,000 years to 8. A civilization that wanted these ships badly enough, for long enough, would not yet find a known law of nature clearly closing the door. It would find an unfinished civilization looking back at it in the glass. Let the great paper ships settle into their drawers now. The pusher plates and the fusion pellets and the trajectories to Barnard's star. Patient, the way good ideas are patient. Waiting in San Diego and London for a century that wants them. But notice what their arithmetic quietly leaves standing. Daedalus flies for 50 years and carries no one. Orion's star voyages last a century or more. Machines do not mind such spans. People do. People are born and grow old and hand what they love to their children. Every vehicle we have boarded tonight has carried, at most, a machine, but the oldest dream of the stars was never about machines. It was about people, looking up from campfires and rooftops and bedroom windows, wondering if anyone would ever actually go. And the arithmetic of the last few chapters has handed that dream a strange and tender problem. Even the mightiest paper starships need decades or centuries for the shortest crossings. A machine can sleep through such a span. A person cannot. A human life is simply shorter than the road. And so, for more than a century, serious thinkers have kept returning to one astonishing solution. If the voyage is longer than a lifetime, send more than one lifetime. Build a ship that is not a vehicle at all, but a world. A vessel where the crew that arrives is the descendants of the crew that departed. Engineers and writers call it a generation ship, and this chapter belongs to it. The idea is older than spaceflight itself. Konstantin Tsiolkovsky, the schoolteacher whose equation gave us the tyranny of the fuel tank, also filled notebooks with visions of vast inhabited vessels drifting between suns, greenhouses and living quarters turning slowly in the dark. And in 1918, the American rocket pioneer Robert Goddard, the very man whose name now sits on a NASA space center, wrote a private essay he called The Ultimate Migration, imagining humanity one day sending its seed outward on immense, slow arcs. He sealed the essay away, reportedly concerned it was too speculative for his scientific reputation, and it stayed hidden for decades, published only long after his death. Even the boldest rocket man of his age kept the generation ship in a locked drawer. That is how large the idea is. So let us walk through such a ship together, slowly, the way you would walk through a sleeping building at night. From the outside, it might be a cylinder several miles long, turning gently as it coasts, because that turning is what presses its people softly to the floor in place of gravity. Inside, there would have to be everything, not supplies for a voyage, but the full standing machinery of a living world, farms and orchards under long artificial suns that dim on schedule into artificial evenings, water endlessly cleaned and returned, the same patient molecules drunk by great-grandparents and great-grandchildren, air breathed and rebreathed across centuries. refreshed by forests planted by people who knew they would never sit in their shade. Workshops able to repair every machine on board, including the machines that repair the machines. A hospital where every doctor was born on the ship. A school where the geography lessons describe a planet no student has ever seen and no student ever will. And somewhere, almost certainly, a quiet room set aside for remembering Earth, with recordings of rain, and crowds, and birdsong, and the particular sound of wind moving through trees that are no longer anywhere nearby. Here the engineering question quietly becomes a human one, because the hardest cargo on a generation ship is not water or air, it is continuity. How many people does a traveling world need? Researchers have genuinely studied this, and their answers do not agree, which is itself worth hearing clearly. The anthropologist Cameron Smith of Portland State University has published work suggesting that a healthy founding population for a voyage of centuries should number in the thousands, perhaps tens of thousands. To keep a human community genetically and socially resilient through storms no planner can foresee. At the other end of the range, the astrophysicist Frederick Marin and his colleague Camille Belufi ran detailed computer simulations of a hypothetical 6,300-year voyage and found that, within their model, under strict rules about health and family planning, an initial crew of just 98 people could survive the entire crossing without collapse. 98 people, or 10,000. The distance between those answers is not a failure of science. It is an accurate measurement of how much nobody yet knows. Because nothing like this has ever been attempted. And every number in the literature is a number from a model rather than from a voyage. But the deepest questions aboard such a ship would never be about genetics. Feel them, one at a time, without any need to answer. The people of the middle generations would be born on a ship they never chose, bound for a destination they will never see, tending gardens for descendants they will never meet. What do you tell a child born in the 200th year of a 500-year voyage when she asks why her whole life must happen inside a corridor between two skies? Perhaps you tell her what is, after all, simply true, that every human being who has ever lived was born mid-voyage on a world already moving, into a story already started, that no one anywhere has ever seen the beginning or the ending of the journey they were born into. That meaning has never once depended on seeing the ending. Our own planet, the pale blue original of every generation ship, has been carrying its crew through the dark for 4.5 billion years. And nobody aboard has ever been asked for a ticket. There is one more turn in this chapter, and it is the strangest one. Some thinkers have noticed a problem almost comical in its cruelty, sometimes called the weight calculation. Suppose a generation ship departs tonight on a 500-year voyage. If, 2 centuries from now, the civilization back home invents something faster, fusion ships, laser sails at full scale, then the new ships could overtake the old ark somewhere in the long middle of the dark. The pioneers could arrive at their promised star to find the porch lights already on, their destination settled generations earlier by the descendants of the neighbors they left behind. Some scholars have argued, only half joking, that the most efficient first step toward the stars might be to wait and grow faster. Others answer that a species which always waits never leaves at all, and that nobody ever crossed an ocean by standing on the shore, improving boats in their imagination. Both sides are holding a real piece of the truth, and the argument between them may be the most human thing in this entire chapter. So let the great cylinder turn away into the dark now. Orchards asleep under dimmed lights. Corridors quiet. A child somewhere aboard, dreaming of a star her grandchildren will finally see up close. The generation ship solves the problem of the road by bringing the whole village along. And it pays for the crossing in the only currency our species has always had in abundance. Lifetimes, willingly handed forward, exactly as they were handed forward on foot out of Africa. But as the arc fades, one assumption we have carried all evening deserves to be questioned at last. We have been taking it for granted that time itself is fair, that a year is a year. For everyone, everywhere, traveller and homebody alike. What if that is not true? Everything we have calculated tonight rests on one silent assumption, so obvious that it feels strange to say out loud. The assumption is that time flows at the same steady pace for everyone, everywhere. One universal clock ticking above the universe. The same for the traveller and the stay-at-home alike. It feels less like an assumption than like common sense itself. And in 1905, a 26-year-old examiner at the Swiss Patent Office in Bern, a young man who reviewed other people's inventions by day and thought about light on his walks home, published a paper showing that it is not true. His name was Albert Einstein. The theory is called special relativity, and buried inside it is the single most generous fact in all of physics for anyone who dreams of the stars. Here is the heart of it, told slowly. Einstein began from something. Experiments kept stubbornly confirming that the speed of light in vacuum comes out the same for every observer, no matter how that observer is moving. Chase a beam of light at 90% of its speed, and it does not recede from you at a leisurely 10%. It recedes at the full speed of light, exactly as if you had never moved at all. That sounds impossible. Like a runner, you can never gain a step on no matter how hard you sprint. Einstein realized that for it to be true, something else, something we trusted completely, had to give way. The thing that gives way is time. For a traveller moving very fast, time itself runs slower than it does for those left behind. Not the ticking of their clocks only, but everything. Their heartbeats, their aging, their thoughts, the cooling of their coffee. The traveller notices nothing strange. Aboard the ship, seconds feel like seconds, and years feel like years. Only in the comparison, only when the clocks are brought together again, does the difference appear. Your first instinct, in the comfortable heaviness of this hour, might be that this sounds like philosophy rather than physics. So let us be concrete, because this effect is not an idea, it is a measurement, repeated for decades, with instruments of exquisite precision. In 1971, two scientists named Joseph Hafele and Richard Keating carried atomic clocks aboard ordinary commercial airliners and flew them around the world, then compared them with identical clocks that had stayed home. The travelling clocks disagreed with the stationary ones by tiny fractions of a second, and the differences matched the combined predictions of relativity for both motion and gravity. Since Einstein's later work showed that altitude tugs at time as well, every day, the satellites that run the navigation on the phone beside your bed experience time at a slightly different rate than you do, and their systems correct for relativity continuously. Without those corrections, your maps would drift by miles within a single day. and in particle laboratories, unstable particles called muons, which should decay in about 2 millionths of a second, are seen to survive far longer when accelerated to near light speed, living on stretch time exactly as the equations predict. To the decimal. Time dilation is not speculation. It is a maintenance requirement of the modern world. Now bring the gift to tonight's question. These figures set aside the long work of speeding up and slowing down, and imagine a ship already at cruise. So hold them as idealized numbers. The physics with the engineering left for later. A ship cruising at 90% of the speed of light crosses 1 light year. By Earth's calendar, in a little over 13 months. Aboard the ship, less than 6 months pass, pushed to 99%. And, while Earth's clocks record just over a year, the crew experiences under 2 months. And there is a second half to that magic, which makes it easier to picture. From the traveller's point of view, it is not only their clock that changes. The road ahead is shortened too. At high speed, the distance itself contracts. So the crew is not crossing a light year quickly so much as crossing a shorter journey at an ordinary pace. Nobody aboard ever outruns light. They simply have less far to go. The two effects are the same fact seen from 2 chairs. Push closer to light speed, and the crossing compresses toward weeks, toward days. Without any flaw, carried to its extreme, the mathematics says a sufficiently fast traveler could cross the entire galaxy, 100,000 light years, within a single human lifetime of experience time, stepping off the ship into a universe 100,000 years older. The universe, it turns out, offers a discount for speed. The faster you go, the less of your own life the distance costs you, and now the price. Because every gift tonight has come with one, the price is energy, and it rises without mercy. The same equations that slow the traveller's clock also make the traveller harder and harder to push. As a ship approaches light speed, each additional sliver of speed costs more energy than all the speed before it, and the total climbs toward infinity as light speed nears, accelerating. Even a modest crewed ship to 90% of light speed would demand energy on the scale of our entire civilization's output for years, delivered somehow to a single vessel, then delivered again at the far end to slow it down, because arriving is only worthwhile if you can stop. Energy is the first and largest obstacle. It is not the only one. Behind it stand others, quieter but just as firm. At such speeds, the thin scatter of interstellar dust and gas becomes a lethal wind, demanding shielding nobody has designed. The engine's own waste heat has to go somewhere, and space is a famously poor place to cool off. Radiation must be kept away from a crew for years on end. Guidance must work when a fraction of a degree of error becomes a miss of billions of miles. Nothing in physics forbids any of it. But energy is not the only thing standing between us and that speed. And it would be a kindness to no one to pretend otherwise. There is one more cost. Softer. Belonging to the heart rather than the engineering. Einstein's gift is a one-way door. A traveller who spends 6 months of her own life crossing to a star, and 6 months coming home, returns to an Earth where years have passed. Friends have aged. Children have grown. The world moved on without her. Not out of neglect, but out of physics. Relativistic travel does not just shorten the road, it quietly rearranges Who will be waiting at the end of it? Any species that one day accepts the universe's discount for speed will have to decide, family by family, what it is willing to trade for the stars. So hold both halves of this loosely as your thoughts soften. The universe has been strict with us all night. Rung after rung, wall after wall, but here, at its deepest level, it turned out to be strangely kind. Written into the fabric of reality is a rule saying the road shrinks for whoever dares to travel it fast enough. We cannot yet afford that kindness. It is there, regardless, verified in flying clocks and falling particles, waiting in the equations like an invitation with no expiration date on it. Every road we have traveled tonight has shared one quiet assumption. The distance itself is fixed. 1 light year is 1 light year, and the only question is how bravely we cross it. But, in the equations, Einstein spent his later life writing the equations of general relativity. Space is not a rigid stage at all. It bends. It stretches. It sags around every star and planet like a mattress under a sleeper. And that sagging is what we call gravity. Once physicists understood that space itself is flexible, a few of them began to ask, very carefully, a question that sounds like it escaped from a dream. If space can bend, can it be bent on purpose? Could the road itself be folded, so that a traveller arrives without crossing the miles between? This final rung of the ladder holds the two most famous answers, and I will tell you plainly, before we begin, what kind of things they are. They are mathematics, not machines. The first is the wormhole. In the 1980s, the astronomer Carl Sagan was writing a novel about humanity's first contact with another civilization and needed his heroine to cross the galaxy without cheating on the physics. So he asked his friend Kip Thorne, one of the world's leading experts on Einstein's equations, what the least impossible way might be. Thorne took the question seriously, worked through the equations with his students, and found that they do contain a structure now known as a traversable wormhole, a tunnel connecting two distant regions of space, a fold in the mattress where two far-apart points briefly touch. Enter one mouth near Earth, drift a short way, and emerge near another star. The light years simply bypassed, but the same equations deliver the fine print. Holding such a tunnel open requires negative energy in a stable, large-scale form that nobody has ever observed or produced. Physicists have measured tiny negative energy effects in delicate laboratory setups. So the concept is not pure invention, but nothing remotely like the amount or the arrangement a tunnel would need has ever existed outside a chalkboard. Without it, any wormhole slams shut faster than light could pass through. The second shortcut arrived a decade later. In 1994, a young Mexican physicist named Miguel Alcubierre, then a graduate student in Wales, wondered whether the warp drive of science fiction could be described with real mathematics. He sat down with Einstein's equations and tried, and to nearly everyone's surprise, he found a solution, known ever since as the Alcubierre metric. The trick is elegant. The ship itself barely moves. Instead, space behind it expands and space ahead of it contracts. So the ship rides inside a calm bubble while the road flows past. Nothing inside the bubble ever breaks the local speed of light. And yet, the bubble as a whole can, in the mathematics, cross a light year in far less than a year. Einstein's speed limit applies to things moving through space. It says nothing about space itself, which stretched faster than light in the early universe and broke no rules doing it. And then, once again, the fine print, sculpting such a bubble, calls for that same unobtained ingredient, negative energy, in quantities that early estimates put beyond absurd and later refinements reduced only to unimaginable. A small number of researchers, including some working within NASA-associated programs, have explored the mathematics and possible tests, and it is accurate to say that no laboratory anywhere has produced or confirmed the ingredients a warp bubble would need. So what do we truly hold? Here, at the top of the ladder, something that has to be described with care, because the difference between two sentences is the difference between honesty and hype. It is true that general relativity contains geometries that resemble shortcuts. It is not known whether nature permits those geometries to form, to remain stable, to obey the deeper rules of quantum physics, or to carry anything through intact. Some theoretical work suggests quantum effects may rule out the useful versions entirely. So the fair summary is not that a door stands unlocked, and I am not going to tell you that it does. The fair summary is that when physicists searched the rulebook for a line reading absolutely never, they did not find one. They did not find a guarantee either. They found open questions, which is what every frontier has ever looked like from the inside. The universe has not said yes. It has, so far, declined to clearly say no. And there are worse lullabies than that. We have now climbed every rung. The walking feet, the wheels and wings, the rockets, the falling probe, the coasting sisters, the sails, the atomic blueprints, the traveling villages, Einstein's discount, and here at the top, the folded roads that exist only on paper. All that remains is to stand at the summit, look back down the whole ladder at once, and answer, completely, the question a child asked at the beginning of the night. Every good question deserves to have its answer, said plainly, all at once, before sleep carries the details away. So this chapter is the summit, the place where we stop climbing, turn around, and look back down through everything the night has taught us. The question was simple. How long would it take us to travel 1 light year? Here, gathered in one place, is the answer. On foot, at the pace our species used to cross whole continents, 1 light year takes more than 200 million years. A span so deep that birds and flowers did not exist when the walk would have needed to begin. In a car at highway speed, about 11 million years. Aboard a jetliner, more than 1 million. In the X-15, the fastest airplane that ever carried a human being, roughly 150,000 years, holding the re-entry record of the Apollo 10 astronauts, the fastest any human has ever moved, about 27,000 years, holding the record pace of the Parker Solar Probe, the fastest object our species has ever built, some 1,500 years, though that speed was borrowed from the Sun and could never survive the open road. And aboard Voyager 1, the true yardstick of the night, the fastest traveller we have ever actually sent outward, with speed it can keep. 1 light year takes about 17,500 years. A crossing that would swallow the entire history of human civilization with room to spare. That is the answer as it stands tonight. and it deserves to be honored rather than softened. If the question is, what can we do right now? The answer is 17,000 years. And nothing on paper changes what is actually parked in the driveway of our species. But the night did not end at Voyager, because the answer has a second half, made of blueprints and verified physics rather than launched hardware. And each piece of it deserves exactly the confidence it has earned, and not 1 ounce more. The laser-driven sail of breakthrough Starshot aims at 5 years for the crossing, at 1/5 the speed of light. Its underlying principles are consistent with known physics. Light pushes. Small things can be pushed hard, but the integrated system remains unproven. Its sail material unbuilt. Its great laser array unfunded. And capable people disagree about whether it belongs to this century or the next. The atomic ships of the old filing cabinets. Orion, with its thunderous heartbeat, and Daedalus with its fusion fire, were calculated at speeds that bring 1 light year down to a decade or so. They broke no known laws of nature, and nearly every major system in them lies beyond anything our engineering has yet demonstrated. The generation ship crosses on a different currency altogether, trading speed for continuity, paying for the road in lifetimes handed forward. And nobody knows whether its hardest systems, the human ones, can endure the trip. And beyond all of these waits Einstein's gift, the verified fact that for a traveler swift enough, the crossing itself compresses so that a light year might cost its passengers months or weeks of their own lives. Energy stands first and largest in the way of ever reaching such speeds, demanding more than our whole civilization currently produces. And behind energy, weight shielding, propulsion, heat, and human survival, none of them is a law against the journey. All of them are prices, and they are the steepest prices physics has ever quoted. So when a child asks the question that began this night, here is the truthful reply. In one breath, with what we have launched, 17,000 years, with what we have seriously designed, a decade or so, if the engineering can ever be built, with what relativity permits in principle, less than a year of a traveller's own life, at a price nobody can yet pay. The answer depends entirely on which verb you choose: launched, designed, or permitted. And the distance between those verbs is not measured in miles. It is measured in choices, in treasure, patience, and nerve, spent or withheld, generation after generation. The universe posts no guard at the 1 light year mark who says never. It posts a price list and lets every civilization decide how much of the ladder it feels like climbing. And notice, as your thoughts loosen, the strange shape of the progress we surveyed. From the Wright brothers' first 12 seconds of powered flight to the launch of the Voyagers took less than 80 years. A single long lifetime contains the whole distance from a wood and cloth machine skimming the sand at Kitty Hawk to 2 spacecraft, leaving the solar system forever. Our species has been asking tonight's question for as long as it has had language, and it has owned rockets for less than a lifetime. Judging our interstellar future by tonight's speeds would be like standing on that beach in 1903, watching the first flight wobble through its 12 seconds, and concluding that oceans would never be crossed by air. We are the Kitty Hawk generation of starflight. The first hop is behind us, coasting past the edge of the solar system with a golden record bolted to its side. The ocean is ahead. No complete path across it has been demonstrated, and no known law has yet ruled every path out. There is one more turn in this night, and it is the gentlest one. All evening we have asked how long it would take us to cross 1 light year, and every answer has been heavy with zeros. But we have been standing at only one end of the road, looking out. All night long we have stood at one end of the road, looking outward, asking how we might ever cross it. This chapter turns around, because here is the fact we saved for the softest hour of the night. The road has already been crossed, not by us, and not once, but constantly, in unbroken silence, for as long as you have been alive. Every single time you have looked at the night sky, you were watching the finish line of the exact journey this whole night has been about. 1 light year, and 4, and 1,000, crossed completely, arriving at your window, ending at your eyes. We could not go to the stars tonight, but the stars, in the only way physics allows, have been coming to us all along. Let us walk this reversed road slowly, starting close and moving outward. The same ladder as before, climbed now by light instead of by us. The moonlight falling across a bedroom floor left the moon a little over 1 second ago. The sunlight that warmed your face this afternoon departed the sun 8 minutes before it reached you, so that every sunny day of your life has been lived 8 minutes behind the star that made it. Already, notice, light does casually what our fastest machines cannot. The distance the Apollo crews needed 3 days to cross. Light crosses between 2 beats of your heart. Now go farther. The next time you see a bright reddish star in the winter sky, it may be Betelgeuse, glowing in the shoulder of the constellation Orion, one of the most familiar stars in the northern sky. Astronomers estimate its light needs several centuries to reach us. Several centuries. The glow arriving from that star tonight left it before the first telescope was ever built, before anyone on Earth had seen the rings of Saturn or the moons of Jupiter, before we knew what a star even was. It crossed the entire span of modern history to get here. Empires rose and fell while it travelled. Sciences were born. Your family's whole story unfolded, generation by generation. And through all of it, that same light was in flight, moving at the cosmic speed limit, aimed at a night it could not know, when someone like you might happen to glance up, and Betelgeuse is still the close neighborhood, on a dark, clear autumn night, with no telescope at all. A person in the northern hemisphere can see a soft smudge of light in the constellation Andromeda. That smudge is the Andromeda Galaxy, and according to astronomers, its light travels for about 2.5 million years to arrive here. When the light now entering someone's eye left Andromeda, our own species did not yet exist. Our distant ancestors were only beginning to shape the first stone tools. The oldest thing your unaided eye can see is a journey of 2.5 million light years, completed tonight, for free, at your window. And here is the turn within the turn. The thought this chapter was built to hold. Light does not only arrive here, it also leaves. The earth shines too, faintly, with reflected sunlight and the soft glow of its cities. And that light departs into the dark at the same unbreakable speed, carrying the image of this world outward in a growing sphere, which means something that is not a metaphor but plain, literal physics, the light that left Earth 1 year ago tonight. sunlight that bounced off oceans and rooftops, and the world, as it was on this same calendar night last year, is at this very moment exactly 1 light-year away. Still going. The journey we measured all night in tens of thousands of years is being completed tonight. In exactly 1 year, by the departing image of your own world. Nothing we build can make that trip yet, but the picture of us makes it constantly, effortlessly, a new copy, leaving every second, so that our planet trails its own history behind it, through the galaxy like the wake behind a ship, somewhere out there, 1 light-year deep in the dark. Tonight is the light of last year's Earth. Whatever your life looked like then, the glow of that evening is out there now, reaching the 1 light-year mark right on schedule. Because light is always on schedule, so the answer to tonight's question has one more layer, the softest one. How long would it take to travel 1 light-year? For our machines, 17,000 years. For our blueprints, a decade. For a fast enough traveler, less than a year of their own life. And for light itself, including the light our own world gives back to the sky. Exactly 1 year, proven again every single night. In every direction. Forever. The crossing we dream of outward is completed inward billions of times over, ending at the one place in the universe where you happen to be resting. Every star you have ever seen is proof that the distance can be crossed. Because every star you have ever seen is a crossing that finished. The sky is not a wall of distant, unreachable things. Seen properly, it is the opposite. It is a record of arrivals. This last chapter has no new machines in it, no dates, and no distances. Everything tonight's question needed has already been answered. What remains is only the quiet work of setting the whole journey down, the way you set down a heavy bag inside the front door, glad to have carried it, gladder still to let it go. So let the ladder dissolve now, rung by rung, in reverse. Let the folded roads close themselves back into their equations. Patient mathematics, returning to the drawer, waiting without complaint for a century with better tools. Let Einstein's swift ships slow and fade, taking their strange kind clocks with them. And let the traveller who would have aged so slowly stay home tonight with everyone she loves. Let the great cylinder of the generation ship turn away into the dark. Orchards asleep, corridors dim. Its long promise kept by people who never needed us to watch. Let the atomic blueprints slide back into their filing cabinets in San Diego and London. Unbuilt, undisproven, at peace in the dark of a drawer. Let the little laser sail flutter down out of its column of light. No heavier than the thought of it. Let the golden records travel on unheard, carrying a heartbeat and the brain waves of a woman in love, out past the edge of everything mapped. Let the falling probe keep falling around its star. Let the old sisters keep coasting. Let the rocket settle back onto its pad, and the airplane land, and the car pull into the driveway and tick softly as its engine cools. And at the very bottom of the ladder, let the walking feet come to rest at last. Somewhere on open ground, under a sky full of finished journeys. None of it needs you anymore tonight. That was the quiet secret underneath every chapter. And it can be said plainly now. Voyager 1 does not need you to stay awake. It will add more than 300 million miles to its journey this year. Whether or not you remember its name by morning, the light from Andromeda will keep arriving, 2.5 million years deep, on every clear night, for longer than our species will exist. And it has never once asked for an audience. Even the image of our own world, 1 light-year out tonight, and still going, carries on, without the slightest help from anyone. The universe runs on scales where nothing is urgent, where a crossing of 17,000 years is unremarkable, and where patience is not a virtue, but simply the way things are. You have spent this whole night in the company of travelers who cannot hurry, and it is very hard to feel behind schedule while keeping company with the stars. Think of who we met tonight, and how little any of them rushed. A schoolteacher who could barely hear, working out the mathematics of leaving Earth in a log house where nobody was listening, decades before anyone flew. A young engineer noticing an alignment of planets that would not come again for 176 years, and simply saying so. Physicists in San Diego and London drawing starships that would not be built in their lifetimes, or their children's, and drawing them carefully anyway. Cave painters working by lamplight on walls they could not have imagined anyone would see, and being seen anyway, 17,000 years later, which is exactly 1 light-year of Voyager's patience. None of them finished anything that night. Each of them simply did their part of it and went to sleep. And the work waited. And the work is still going. If any single thought deserves to follow you across the border into sleep, let it be this one. The distance was never a rejection. 1 light-year, with all its trillions of miles, is not the universe telling us to stay home. It is simply the true size of the room we live in. And knowing the true size of your room has never once made a bed less warm. We are a young species. The door is not open yet. But you heard the whole story tonight. And you know what we found at every rung. Not a wall that says never. A price list. And a species that has barely begun to save. So let go of the question now. It was a good question, the kind a child asks, and it was answered as carefully as our century knows how. Whatever your own tomorrow holds, it is closer than any star, and it needs nothing from you until morning. Your breathing has probably already found its slow rhythm. Your thoughts are probably loosening at the edges, drifting the way they do right before sleep. And that drifting is not a failure to pay attention. It is the whole point of this hour. The only journey left tonight is the shortest one of all. The soft slide from resting into sleeping, which asks for no engine, no fuel, and no courage at all. You have everything you need for it. You always did. And that is where we will leave things for tonight. What can stay with you, if anything, is only the shape of the night. Slow, then faster still, and then, at the very top, the quiet discovery that the road was never empty at all. That light has been crossing it the whole time, finishing the journey at your window again and again, asking nothing of you in return. If tonight's journey brought you a little wonder, or made the dark outside your window feel a little more like a place you understand, a like or a subscription helps these slow science journeys find their way to more people looking for exactly this kind of quiet. Only if you wish. There is no pressure anywhere in this room. Wherever you are listening from, the room around you is real and close, and yours. The stars will keep crossing the distance, whether or not we ever learn to follow. Tonight, no one has to follow anything. Your only destination is sleep. And unlike every journey we measured, this one you can finish before morning. Good night. Rest well. 1 light year from last year's light.